Hello Lars.
Hey Thomas.
Hello outside world. As you know, we're all in a corona situation that is critical for us all, but in fact I want to have a warm welcome for you here at Technica Engineering. Today we want to give you an overview about our lessons learned the last 10 years for Automotive Ethernet. I want to give you a short overview who we are, what we did. So I don't know if you know that one of the German OEMs in the year 2008 started with Ethernet for a car interface connection. In that case, I was responsible having the first connection to a car. We launched this car in 2008, but it was not good enough for us. We want to have more. We want to have Ethernet inside the car up and running with applications and functionalities. And that's why Lars came in place. And we were introducing a full communication system at the German OEM. Lars was the one who was responsible for the someip stack at all. I would say he's one of the inventors of this someip stack system, and me as a person, I was responsible for bringing the thing up and running in a car. And of course, you can expect that not everything was working perfectly. So we have our lessons learned, but not only in that case. When we're now working for Technica Engineering, we see a lot of other use cases where we see pros and where we see cons, and where we still have our lessons to learn. And today we want to give you some information what we did. And yeah, we will start now.
So let's start. We have selected 10 of our lessons learned over the years, and as you can imagine, we had quite some things to choose from. But for 25 minutes, we figured those 10 are the things we can show you the most. Let's start with the communication stack design. In the communication stack, we have different protocols you will use in the car for basically exchanging the data. In those protocols, you have some choices. You can use IPv4, you can use IPv6, you can use AVB to transport the audio and video data, or you can use something else like RTP. At the end, different OEMs took different choices, but that leads to some problems. We have seen that if OEMs use a new protocol which no one has used before, the quality of the implementations they get is lower because nobody has tested it before. So if you choose something that someone else has used, you have advantages. The implementation is better, it works better. So we recommend don't try to compete on your protocol stack, compete on the applications and things you put in your car. So lower the complexity of the stack and stay with the mainstream if that is possible. So, back to Thomas.
So the next topic in our agenda are gateways. Gateways connecting the worlds. Why do we say worlds? So when we introducing Ethernet, we already know that there's a big difference in types of communication from the classic bus systems to Ethernet. So in every design of any OEM, you will see an issue on gateways. But the question is, okay, how are the different options that you have to connect classic bus systems to an Ethernet system? And in this picture there's only one direction shown from CAN directly to Ethernet, but of course it is working vice versa, the same way around. And in that case you have three possible solutions. You have a solution where you simply say you make a kind of application layer gateway where an application converts the informations that has to be, let's say, bridge between the two worlds, and this is a solution of a kind of application layer gateway. Then you have another solution where you just, let's say, you grab all informations, all bus informations from the incoming bus and place them together in a packet and transport them over, for example, a someip service. And in that case, you could really wrap them into a service. This is another solution. A third solution that is available is that you simply copy the data that is coming from the source bus over a simple lower level UDP a telegram directly in the Ethernet world. So the question is, what approach do you want to take? And now you will see that in the end it all turns out in a mainly distribution problem. So the gateway has to translate a lot of informations, and if you have to do this translation in a local ECU, you will see that this ECU, so this ECU is the gateway, you will see that the increasing number of translation that is necessary. You will see that this device will automatically come to a bottleneck. So that means the risk is very high that this device will limit your scalability in your network. Another big problem is that you have to deal with a lot of problems that is needed when you bridge the two worlds. For example, you have to take care about the safety solutions that has to be bridged between these two worlds, and this has to be done in this gateway as well. So in the end, based on today's power of ECUs, we would rather say our lessons learned case is really to have this gateway concepts to be absolutely simple. So lesson learned in that case is be aware of the scalability of your gateway concept and prefer simple concepts. So the next point on our list is the network design. Especially we want to focus today about the different link speeds that is possible on Ethernet. As you know, Ethernet has a wonderful full capability that you can mix different link speeds. So this is one of the motivation to say when you start with Ethernet, you can just start with 100 megabit. Then you will have maybe a new, not maybe, absolutely sure today it's there. You can have 1000 megabits, so a gigabit link or multi-gigabit links, or even you can go down and downgrade it to 10 megabit. So it's a perfect situation where you can expand your system. But let's now imagine you have a 800 megabit leader stream that hits a small ECU and with a 100 megabit link. So this might not end well for the ECU and neither for the network. So that means you have to be very careful now when you start mixing the different speed grades. So the thing is, your automotive network is in great danger since switches could start dropping packets, or you still lose data because the link is overflown. So that's why it's really important to be clear what you have to do in the network design to deal with different link speeds. Yeah. So what you can do is, for example, you can separate your network into smaller pieces using VLANs, multicast groups, etc. So in that case, you do not want to have a video stream hitting a router, and you can prevent it by using these mechanisms. Another way is having traffic shaping on all the senders and the switches. So you have to give really the switches and the systems room to breathe. So that means you should not waste the time slots that the switches have to deal with different traffics. So then what you can do is you can police traffic on the incoming switch ports to prevent your network from from, let's say, a misuse in that case. Or in the other case, you have to design the topology right. So that means daisy chain that was good in the past because you do not need so many switches. It's sometimes easier, have a scalable, we thought we have a scalable system, but in that case it's very bad because then you will see by having these daisy chains, these problems will more and more start and kill your network if you don't be careful. So there is still an open problem what we see, that a lot of SoCs, they have no direct hardware support for traffic shaping. So, and this is a critical path because traffic shaping in software is always very critical and needs a lot of resources. So our lessons learned in that case is mixing link speeds can kill your network faster. What you have to do, you have to engineer your network.
So the next thing is the power cycle. In automotive, startup is a really critical phase of the system. You don't want to wait for your car to start up for like many seconds. You don't want to, go into car and then have to wait like 2 minutes as for your wait for a PC. So we really have to take care of startup. If you start up the system, starting up the software stack is one of the problems you have to solve, and starting the links as well. So you really need to design the timings of the implementations, like for instance, someip service discovery. And don't forget, your security protocols take some time as well. But Thomas told me always, don't forget shutdown and restart, because If you can make the startup, that's one thing, but it gets worse on shutting down and restarting. Restarting basically means you stop the shutdown and start again, right? So you're getting in trouble there. What happens here is the following. If the ECU shuts down, you want to make sure that you clean up all the state, the distributed state in this overall system. You want to make sure that your peers have the possibility to clean up. If you interrupt that, of course, you might be in an intermediate situation where you have some old state and some new state, and that can get really wrong. So one of the things we have learned is really make sure you have a detailed design and complete requirements for startup, shutdown, and restart, and test that as much as you can. And after that, you probably want to test it again. The next thing we want to look at is safety, redundancy, and Ethernet. In the automotive world, we assume that a communication system is a gray channel, and we use end-to-end communication protection. Based on the AUTOSAR standard, you probably have seen Alive and CRC on messages before. So what you do there is you check if the communication channel works, and if it doesn't, you know that, and you can react on it. You fail safe. But with the new autonomous driving use cases, that's probably not good enough anymore. We need to fail and stay operational. So what do you do here? At the end, the OEM needs a system-level operational system, so you need to have system-level redundancy. If something breaks like a radar sensor, you still want to make the system still work. So basically, people started to discuss redundancy in all different parts of the system. In the communication world, people were discussing having, for instance, PTP or GPTP to be redundant, Ethernet links to be redundant. But after all, if my sensor breaks, having a redundant Ethernet link to the sensor does not help me at all. So make sure that you're not the guy with the hammer that treats everything like a nail. Because we network guys seem to be that guy at times. So try to not solve the redundancy on the local level, like on Ethernet or on the PTP. Think globally, look at the system level redundancy and try to solve the overall problem there.
So the next topic in our agenda is always a fight between an application developer and a network developer. So an application developer won't have no limitations at all. On the other hand, the network developer want to have a stable and predictable network. And these two, let's say, requests are always in a kind of fight. So the thing is now to say, how can you control this fight, or what kind of solutions can you have? And in that case, somebody will say that's not a problem, but it is. Because there is a situation where you have cyclic or audio and video traffic. This is rather easier because in that case you have a stream. The stream is well controlled, the audio is set up, and the cyclic message coming from cyclically on any sender is well understood. But the problem is, as soon as you go to event-based messages, and in Ethernet areas we have a lot of event-based messages, this might be much difficult to design this type of communication scenarios. So that's why what we learned, it is very important to have a clear interface between these two worlds. And everybody, or not everybody, so the application developer and the network developer can focus in the area. So one solution to get rid of these problems is to cleverly construct virtual pipes where you allow an application engineer, an application developer work in their own pipes, in their own areas. And this area is isolated, or this pipe is isolated from the rest of the system. This can help to make this better. So our lessons learned is really in that case to say, divide the realm of applications and the network, and cleverly construct traffic aggregates and classes that can really help to stabilize the situation here. So now in the end we have to talk about mainly simple thing, what you expect, testing. But testing is very important if you have no time to waste. So do you have to have time to waste in your development cycle? Within the increasing complexity of a system and fast integration cycle, you want to be more agile, I think that's clear. But if you don't be careful, you will see that your test process can slow you down tremendously. So wasting time in that case means completely testing ECU software is done first time at the OEM. That is today's scenario, you could see this. then integration of the Ethernet cluster for the first time in a vehicle is even today sometimes reality. We've seen it in some of different use cases. So our lessons learned in that case, or we have a lot of lessons learned in that case, is first of all a front loading, the testing at the supplier level. You have to control the testing, and you should not mix the implementer and the tester. And another big lessons learned in that case is that you should really front load even the integration of an Ethernet cluster. Create a setup to focus on the Ethernet specific integration before the system and the devices move to a vehicle.
So after testing, now the next thing we want to look at is recording the communication. Every mile you're driving with your test cars is important. So you want to make sure that you capture all information you can get in order to find problems later. But how do you do this? How do you record the data? What do you have to look at? And what the first thing is, of course, you want to record all your bus systems like CAN, you want to record FlexRay and LIN, and also, of course, Ethernet too. And in addition, you need to record the metadata. Record on which link it was recorded, the packet, on which direction it was traveling, and have some precise timestamps that are coordinated over all your equipment. Another thing we see often is that you don't record the startup because your equipment misses the startup. So make sure that you figured out a logging setup that at the startup time you don't lose a packet. You want to record all the startup and all the situation with a lot of traffic if the system is stressed a lot. If you take a state-of-the-art solution, you should look for a logger that implements a high-precision time sync to synchronize all attached equipment. You want to look for capture modules that collect data or metadata for the logger to record. And you want to make sure that the capture modules or the logger, or both, buffer the startup for you. After all, our lessons learned is specify your vehicle logging setup based on state-of-the-art technology. Okay, now you have recorded your data in the car and you have to store it. But what is the logging format you want to store it in? And how do you do that? If you look at automotive standards, you find out that the MDF is in the new version, MDF4, allowing to store bus data and logged Ethernet data. So we looked at that and we're implementing a solution for that. And what we found is really bad at that point of time. There were big gaps in the specification. There's even a tool to check your implementation which has other gaps as well. So we tried out different other implementation of other vendors and found out that they're often not compatible to each other. So the MDF format currently does not seem to be a good fit. Some customers use proprietary formats like an ASCII-based text-based format or a binary format. Just make sure if it's a proprietary format that the specification is open to all you implementers, because if not, you probably end up in a single vendor log. Nobody can build a good implementation without having access to the specification. So at the end, you might want to look in open formats like the PCAP and PCAP-NG that are specified openly, and many implementations are already existing on which you can download from the internet. You find open source tools that already implemented, good libraries that exist. So that is a much better solution in our view. And at the end, we even looked at converter solution, because if you're now thinking, I'm using my proprietary format, but convert to PCAP and PCAP-NG, we found bugs in proprietary converters as well that made it really hard to save all the data at the end. So our lessons learned here is support well-specified open formats like PCAP and PCAP-NG. After having recorded the data and stored it in the right format, the next step will be to look at the data. So what is the appropriate analysis toolchain to do that? When you look at problems in your stack, you get lost without the right tool. Not all tools will work for every problem you have to solve. So what's important here is you need to have a tool that's available to you when the bug occurs. So make sure that the tool is already available when development starts. And of course, if your developers are working on like a head unit or like an autonomous driving computer that is based on Linux, why would you make them use Windows tools for that? Give them the choice of the platform of the operating system for their tool. We are doing a lot of stack testing and we know a lot of stack developers. So what many of those do, they use the open source Wireshark because that's still the reference. It has thousands of protocol implementations in there, and due to a lot of work we did and others, someip, NM, DLT, DOIP, TCMP, our new logging protocol, MQTT, IPsec, TLS, MACsec and others can be supported in there, or are supported in there. For application developers, you might want to use a different tool, but that's your choice. Just make sure that you follow our lessons learned. Never trust a single tool, support different operating systems, and protocol support and configs for that should be ready when the project starts. Okay, now we have time for a short summary. On your way to your SOP, there might be multiple pitfalls and problems you might run into. Today we have presented you with 10 of the lessons learned of our more than 10 years development of Automotive Ethernet. And if everything goes well, we'd say enjoy your relaxed SOP. Since this is a virtual event, we know that it's very hard to get in contact with us. So we have posted all of our contact information on this slide. You might want to send us a postcard or call us or send us an email. After all, stay connected.
And of course, stay safe.